Hi, everybody. So, show of hands, how many people have seen me yet once before? Maybe twice, maybe. So I don't even have to give this talk, right? You already know what I'm going to say. This is really cool. So I'm supposed to give an update of what I found in Owasco Lake last year, and I'll add a few other things to that as well, and see what happens with what's going on. So basically, all right. So start with a slide every year where basically it showed that things weren't so good in Owasco Lake, and it might be tied to a whole host of different reasons. They've changed over time what I think they are, but there's reasons why Owasco Lake is that circle way up in the upper corner showing some of the worst water quality in the Finger Lakes region. Because of that, then I was able to get some money out of either the Emerson Foundation or from the state or from some other groups to be able to look at what actually is going on. You know, first you raise the alarm without any data, then you go out there and collect some data and then try to figure out what's going on. So in 2006, which suggests I've been doing this way too long, I took a bunch of water samples from the lake going from the very northern end of the lake down to the southern end of the lake down here. These 5 sites at the end are right along the Owasco Inlet, looking at total phosphorus, which is the living nutrient that goes into Owasco Lake, and it showed that there was significant, very high concentrations of total phosphorus down at the southern end, right next to the major stream that empties into Owasco Lake, so it suggests that there's some sort of connection. Also noting that there's huge variability down at this end, and was easily explained by whether or not you were sampling within the plume, which has a lot of phosphorus, or outside the plume, which is more normal lake and not a lot of phosphorus. That convinced Senator DeZolio to get me more money, which is good. I did out in 2007, and the results for total phosphorus are down in the lower right here. And you notice that all the numbers are a little bit smaller, especially down at the southern end. I remember that year during the public presentation over in Emerson Park, I was shitting bricks. I had rested my entire case on, oh yeah, rivers bring in a lot of nutrients, and I couldn't find any at all. So something must have been going on. That something that was going on is between the 2 years. I was also looking at some stream data between the 2 years. 2006, you had significant loading of phosphorus. This is dissolved phosphate flowing in 2006. That loading decreased significantly in 2007. The main difference between the 2 years, 1 year was really wet, and the next year was really dry. So it suggests that there's a lot of runoff that's bringing non-point source nutrients into the lake, and if you can control the rain or the cold or anything else, then you have a good chance of trying to improve water quality in the lake. One thing that has happened very effectively is the early years showed that the Groton wastewater treatment facility was adding to the nutrient problem for the southern end of the lake, and DEC decided to put more stringent controls on what they can put in their effluent, and since then they've been doing a really good job. So hats off to them spending a little bit of extra money to help clean up your lake. What these nutrients will do is they can enter a very simple nutrient cycle. The dissolved nutrients come in, they are taken up by the plankton then feeds the rest of the ecosystem. When those organisms die, bacteria can decompose all those nutrients and put the nutrients back into the water column for then plankton to come up again. And in normal systems, there's a little bit of nutrients coming in by streams, maybe it's the atmosphere, and then you have some nutrients leaving by the outlet or being buried in the mud, so it seems to be relatively balanced. However, if you add a lot more nutrients, as shown in this graph, all those boxes tend to get much bigger. And as these boxes get bigger, different algal forms start to form. You can get weeds growing off the bottom, you can get blue-green algal scums and other things. The bottom waters can start turning anoxic and other things. And it doesn't really matter where that organic matter source or that nutrient source comes from. It could be from animal waste, it could be from soil erosion, it could be from human wastewater treatment facilities, it could be from septic systems. It could be from drainage tiles going into ditches, which then drain into nearby streams. Doesn't really matter. It's just that that total load then starts degrading water quality that's in your lake. All right, so last year, busy year, thanks to a number of grants from a number of different people. I did the normal lake and stream watershed monitoring that Cuba County's been supporting for now many, many years, and I just heard the contract's been going through to work on 2019, which is good. The Emerson Foundation worked on the second year of a 3-year project, which helped deploy the water quality monitoring buoy that's out in the middle of the lake, and I'm doing a bunch of nearshore work along the lake as well. And then AWA gave me a bunch of money as well, which is cool, that tried to look at the mitigation technology for blue-green algae along 11 shoreline sites around the lake. Very interesting project, which I'll get to report on here at the end of this talk. Instead of leading up to the story and then concluding that yes, rainfall is the prime control, I thought I'd start out at the very beginning and show you how rainfall changed over the past few years. And there's 3 bars for every year. We have spring, summer, and fall, basically. And you notice that 2011 seems to be a quite rainy year. 2014 and 15 also were quite rainy years, especially in the spring. Look away over there in 2018. Very dry spring, dry early summer. So I ask you guys, should water quality have improved in the lake? Or should water quality have declined in the lake if there was less runoff coming into from the watershed into the lake? So what do you think? Okay, so let's see if the data shows some of that, right? So start with the stream monitoring. I was focusing primarily on Dutch Hollow Brook, which is up in the upper right there. I also took some samples, one sample from the Huasco Inlet down at the southern end, and then there was a couple of small tributaries along the western shore, right at the end of Fire Lane 20 and also along the end of Fire Lane 26, just to see what the relative contributions to some of these things were in terms of nutrient loading and other things. In 2018, here's stream discharge numbers. Here's Dutch Hollow Brook and all the different sites working your way upstream up to here. Here is the inlet at Moravia, and then there's the 2 creeks along the western shore. All these plots will have the same order of sites. Here's 2018. Notice the top number is still under 2. Here's a wet year where the top number's at 5. Significantly more water flowing down these brooks, and when it's wet, with that water comes a lot more runoff. With that more runoff comes a lot more nutrients going into the system in 2011. But 2018, it was really dry. Not as much water, as dry as, say, 2012, which was also a very dry year. And not much happened in that year in terms of degrading water quality in the lake. If you look at nutrient concentrations going from, here's the average lake, here's the input from Dutch Hollow Brook going from downstream up to upstream, there's the inlet, and here's the 2 small creeks on the western arm. I will say that some of these small creeks have significant nutrient concentrations, but when you multiply the nutrient concentration times the flow, the total amount of nutrients going in per year is small, because the flow is so small. But then you step back and you look at all the number of small creeks that are on the western arm of the lake, there's a lot of them. So you total them all up, and it equals one of the bigger watersheds in terms of its total loading into the lake. Dissolved phosphorus down at the lower right. Here's total phosphorus up in the upper left. If you look at nutrient fluxes in 2018, relatively small compared to wet years. The inlet has a lot more because there's a lot more water coming down it. And here's these 2 small tributaries. The flux of nutrients coming in from the small ones are small until you add up all the little ones together, and it tends to be relatively equal to a big one. There's different time scales. We're talking about year-to-year change in rainfall, a lot of rain in the spring or a lot less rain in the spring. You can also look at events, individual events. And here we have Dutch Hollow Brook down by Route 38. There's the road. Here it is right after a rainstorm. Here it is after many days of being dry. Significant difference in, this is really turbid, full of nutrients. This is unbelievably clear, not very many nutrients at all. You can start measuring that if you have the stupidity like me. You can get a sampler shown in the upper right, which then can collect a sample every however many hours that you want. Lately I've been doing it every day, a sample a day, analyzing it for all sorts of things. And then you compare, here's flow in the red, and the green is concentrations. And these concentrations for sediments go sky high whenever there's a rain event, but only when there's a rain event, which then leads to the conclusion, if you can control runoff from rain events, you can reduce the major contribution of suspended solids into the lake. The same is true for total phosphorus as well. If you compare 2018 to a wetter year, notice there's a lot more events here in the early spring than what we had in 2018. So it's 2018 was significantly lower in terms of its contribution. If you total up in kilograms per day for sediments and or phosphorus, the phosphorus numbers and the sediment numbers are a lot lower. But still, if you look at just the events themselves are providing about 90% or more of that load in that given year. So the events are very significant. And if you want to start controlling things in your watershed, start working on controlling those events through buffer strips or maybe remediation of the outlets of tile drains and other things along those lines. You can, I'm always asked, what are the relative sources of things? So I've been trying to estimate it as best I can. Here it is from 2011 going all up to 2018. There's a mean at the very end. The black bar is how much the mean that's going out to the lake. It turns out that about 90% from here up to that green line, that's what comes in from streams. So most of it's non-point source entering to the system. The blue down below, municipal wastewater treatment facilities, this I have a very good number on. I believe that number. All the rest of these are estimates. Septic system loading at the very top is what's coming in from atmosphere. Notice that the human inputs are basically constant, going all the way across. Doesn't matter if it rained or not. They're still constant. Whereas these riverine sources, they go up and they go down. They go up during wet years, and they went down during dry years. 2018 was relatively dry, so it's been down. One last thing to point out about all this is, if you look at everything that's coming in compared to everything that's going out, on average, more comes in than goes out, so that means that we're adding more nutrients to your lake. That means it's going to progressively get greener and greener. All those little boxes in that nutrient cycle are going to get bigger, to the point where perhaps you'll get blue-green algae blooms. No, not perhaps, you're going to get them. You got them. Things that you can do about it. Well, if rainfall intensity is critical to the delivery of these things, you try to reduce that. You could work on lakeshore septics, although we're doing a really good job in this watershed for septic system control. Work on roadside ditches, because they enter into the streams and drain the farmers' fields and other things. If you could work on collecting the influent from drain tiles, that would be really good. There's a drain tile shown over in the lower right over there. Best management practices, more responsible manure spreading, and so on and so forth. There was a talk I heard from a gentleman in Pennsylvania who has a material that he makes that will absorb phosphorus out of flowing water. It's nanoparticles. Nano means it's got huge surface area for its mass, and it can absorb a lot of phosphorus. And then when it fills up, he can take it away and then take the phosphorus off the particles and reuse them again, and sell that phosphorus for fertilizer for someone else. Might be something well worth working on in this part of the world. In terms of water quality in the lake, two main sites, Site 1 and Site 2 out in the middle of the lake, my monitoring buoys in between. Then there's a bunch of other sites that the Emerson Foundation's been supporting for me along the shoreline. Not quite shown here, but they start here and work up the shore, and then go to the other side and work up the other side of the lake, tried to look at differences between open water and shallow water luminology in the system. One thing to talk about first is CTD profiles. This instrument here gives me profiles from the lake surface down to the lake floor of things like temperature, the salinity, the amount of oxygen in the water, the amount of light in the water. This is on a logarithmic scale. The amount of algae in the water, and also the turbidity. Very classic profiles that you'll see from being a relatively dry year. Temperature never changes. The salinity rarely changes, although the decrease through the summer gets smaller. Dissolved oxygen, it didn't change as much as it might during a wet year. The amount of light, if there's more algae, the light doesn't penetrate to quite the same depth. Wasn't as much algae in the water column last year because it was dry, and last but not least, a lot less turbidity in the water column as well, compared to a wet year which has a lot more turbidity, especially along the lake floor at some of the sites, and more algae in the water column and other things. So those are CTD profiles. Looking at Secudus depths, which is that round disk that you see over here, one of my students is lowering. You lower that down until you can't see it. You measure that water depth. The deeper it goes, the clearer the water. Well, it turns out that the average from last year, which is over here, is in general deeper depths than the year before. This is probably because the lake was less green, less algae, because there was less things washing into the watershed, because it was less rain. Other things that sort of mimic what's going on, total phosphorus also took a slight decline, but it's not that big. You look at chlorophyll concentrations. Chlorophyll concentrations also took a slight decline, but it's not a very big decline either. Oops, there we go. If you then rank some of these different water quality parameters, you'll notice that for Owasco Lake, there's 2017, there's 2018. We've improved in water quality because water quality improves down in a downward direction. That's true for many lakes. So you go to Canandaigua, it improved. You go to Cupid, it improved. Seneca, you go to Cayuga, it improved. Owasco improved. Skineados improved tremendously. Not quite so much in Atisco, but a lot of lakes around in the region, suggesting that it's a regional phenomenon, suggesting that perhaps the decline in rainfall was region-wide, and a lot of lakes were improved because of that. Plankton concentration was pretty much the same. The big difference was there was a species, a diatom, which was much more prevalent last year than any other year that I've been working on the lake. I don't know why. Maybe Kim Schultz can tell me why, because she knows more about plankton than I would ever want to know. And then I started flying drones. I borrow it from a colleague of mine. The standing joke is, if I crash it, I pay for it. I haven't crashed too many of them yet. They seem to like trees. I don't know why. They seem to like water. I had one, I took off from a steel boat, and the steel boat messed up its navigation system, and it took a nice sharp bank, rammed its way through the railing of the side of the boat, and then went into the lake before I could even do anything. Like, oh my God, look at that, that's amazing. And then I saw it sink down to the lake floor, and it was only about 100 meters deep there, 300 feet, so that's the end of that one, unfortunately. 2017, you always got a good chance of finding blue-green algae. That's what all this green scum is. This is in front of Jim's house. But then you go back in 2018, crystal clear. I had a hard time finding blue-green algae at the sites that I routinely monitored. You go to the open water. This is the open water out in front of the yacht club on the eastern shore of the lake. They were testing some of the mitigation technologies. They had a bubbler system here and a bubbler system there. And it appears to me that this bubbler system made enough waves that propagated out from where the bubbles were coming up to the surface that it pushed the blue-green algae away from those bubbles into a ring all the way around. But the concentrations were really low enough last year in all the sites that I was measuring that you really couldn't come up with a statistical difference to say, yes, indeed, that bubbler system was working. They also had another system here, an ultrasonic system that was right there. And I don't see much difference around it in any sort of diameter whatsoever. So maybe it was doing something, maybe not. It's hard to say. So that's what the drone could do for me. We're working on other things to actually figure out from the spectral images what's there to actually get concentrations of algae. It's a lot harder than someone would want to think. You look at Flora Probe results. Flora Probe is a really cool tool. It's this one over here. It costs about as much as that, the CTD over on the other side. You strap them together, so if you lose one, you lose both, and then I guess I'm out of business, who knows. That's another instrument I'm borrowing from somebody, so whatever. All these graphs, different dates. You have the offshore average here, then you have all the nearshore sites that I was doing for the Emerson Foundation, trying to look for blue-green algae. And blue-green algae is in this dark blue, which is really fuzzy down here. Notice that there's more light blue as you work your way through the summer. So late summer, early fall, more blue-green algae. But it wasn't as significant as years in the past. We just didn't quite have the blue-green algae last year as we did other years. Now, on a few days, there was good blooms, and they got measured and detected, but perhaps not as many. Here's the actual data coming from DEC. Thank you very much for allowing me to use it. Notice most of the blue-green algae, again, is located along the shore. The distribution usually used to be along the northeast shoreline. There's more detected blooms over on the western shoreline. The big difference that I saw between the years, usually the wind's a little bit west of south. Last year it was a little bit east to south, so maybe it was blowing more stuff over onto the western shore in 2018 than other years. If you look at mean blue-green algae concentrations by this nearshore monitoring, it's steadily gone up and then plateaued in the last couple of years. If you look at the toxin concentrations, the mean toxin concentrations, it too has risen significantly. That's unfortunate. If you look at the number of reported blooms, started low 2012, peaked in 2016, and now it's declined. That could be an artifact of who's looking and how often they're looking. But you guys are really good about looking for blue-green algae, so I don't think that's coming to play here. So maybe we're not getting as many blue-green algae, or maybe the lack of rainfall had something to do with nutrient delivery and stymied the amount of blue-green algae that happened in the lake. I do know, where I monitor the lake using that buoy, which then takes a water column profile twice a day and takes all sorts of meteorological information, no blooms whatsoever. Part of it is the most surface sample is about 1 meter deep, 3 feet deep. Blue-green algae float at the surface when they bloom. So maybe I'm missing them. But I've had a lot of people give me reports. Oh yeah, we went out to your buoy, we didn't see anything. Or we went out to your buoy, we saw a green scum, which my buoy didn't detect. It's just, basically I can't bring this upper part of the sensor out of the water, and this is about 2 or 3 feet down. So that's what I'm starting to detect at the uppermost depth with that device. It's unfortunate. The other thing I can note, I'm sure I said this before, don't bring a tall mast underneath the bridge in Emerson Park when it's springtime. In the fall it goes right through because the lake level's down. It doesn't go right through during the spring as easily. There was another buoy in the lake. The USGS had another buoy. I'm sure Tony and others will be talking about it. It's really good for me because I can compare my results to its results. So in dark blue is its results. This is temperature at the surface. In the crosses is my results. So they're doing a really good job, right? Or I'm doing a really good job, or somebody's doing, maybe we're both doing a really good job. Down at the bottom water, so at the bottom water for the USGS buoy, which is way up at the northern end in shallower water, it's in blue. At the same depth that my site is in yellow, notice their site had some excursions getting to warmer water. Those excursions are related to internal safe activity, where the thermocline, the boundary between the warm surface water and the cold bottom water, starts to oscillate back and forth after a big wind event. And as it oscillates back and forth, it will impact, as shown by this cartoon, if you have that boundary oscillating back and forth, where my buoy is at and where the USGS buoy is at, well, this tilting will influence that northern site a lot more than my site. And that's the difference that you're seeing between the two. That's all I wanted to say. If you look at turbidity, this actually highlights some really interesting information in that you look at my buoy site, it's in the yellow, going across. This is down near the lake floor for the other buoy, so it's at the mid-depth site in my buoy. If you go to the USGS buoy in blue, notice that there's some significant turbidity events. Those turbidity events can be related to that SAISH activity I just talked about. So if you line it up with deviations in the temperature, notice some of these spikes line up nicely, but not all. So not only is it probably internal SAISH activity, but maybe just wind and waves. There was a day last year when I tried to go out on the lake in my pontoon boat, and after the third or fourth total swamping, waves coming over the top of the bow, running down past my feet and behind the order, we decided to turn around. But you can just imagine what it's doing to the lake floor, right? And as we were coming back into Emerson Park, I saw the state trooper there with his binoculars. He was making sure that I made it all the way back safe, so thank you very much. My wife appreciates it. Maybe my kids too, you never know. One thing I did do is have temperature sensors along the near shore at a number of different sites. And in the light lines are all these near shore temperature sensors. In the heavy blue is what's being recorded at the buoy site out in the middle of the lake. And notice that there's really good consistency. It might warm up a little bit more or cool down a little bit more in near shore sites, but you can explain that away. More importantly, though, is I've also plotted on this is when there was blue-green algae blooms along the near shore in these crosses. Every time there's a down dip in temperature, there always seems to be blue-green algae blooms. And that happened in 2018. It also happened in 2017. A dip, blue-green algae, a dip, blue-green algae, another little dip, blue-green algae, another dip, blue-green algae, another dip, blue-green algae. Which got me to thinking, what then can make temperature decline? Well, a big wind event will mix up the water, bring colder bottom water up to the surface. With that wind usually comes rain. The rain's usually colder. It can make the surface water a little bit colder. So events, mixing events, might have something to what's going on in this lake and related to blue-green algae blooms. Part of the work last year we looked at taking daily photos along the lake shore. There's all the sites shown in the map over there, 11 sites total. And what they showed me was something really interesting. Day before, day of a bloom, and it looks like a nasty one, day after. These things are really sporadic. Here's another site. Day before, day of the bloom, day after. And then some of these homeowners would tell me, oh yeah, we missed the bloom that day, suggesting that they're really short-lived, a couple hours, coming when conditions are perfect for blue-green algae. Calm, still, sunny, and then they bloom. As long as there's also enough nutrients around for them to bloom. You put some of their data together, and this is what it looks like. They started taking pictures at the end of July. They went all the way through the end of September. The blue boxes is when they took pictures. The yellow boxes they forgot for some reason, who knows. The red is when they actually detected blooms in their photographs. This was all compiled by Peter Rogers, God bless his soul, because it's a lot of work. Notice it's still sporadic. Not every day do you get a bloom. Better yet, when you do have a bloom at many sites, a bunch of others don't have blooms. So not only spatially, but also temporally, they're sporadic, maybe they're neurotic, who knows. And then you compare it to some of the other places where the monitoring was for blue-green algae. They had a bloom, but none of my sites did. They found a bloom, but none of my sites did, all the way through. It was only on this day that everybody had seemed to have a bloom, and this day over here. So there's something coming on with that sporadic nature, which suggests that something will trigger them, they will come and bloom and then die off. So we got to look for that trigger in all this. And that trigger, I think, is related to the dips in dips in temperature. Dip in temperature, a bloom. Dip in temperature, a bloom. Dip in temperature, a bloom. Another dip, another bloom. Another little dip, and then another bloom. and you compare it to other meteorological data that the buoy provided, blooms come on a calm day. And there's another calm day shown in the crosses. And there's another calm day. There's a third calm day. They really like, except for this data point over here. I wish I could just get rid of it, but anyway. Except for that data point, they always seem to like calm days. It turns out for this data point, where it bloomed, it was calm because of shoreline conditions protected that part of the shoreline from the waves and other things, so they could come up and bloom. What's also interesting is we're coming after this dip, so maybe this dip, this mixing somehow stirred things up to get things going, but you then waited for the next really sunny day. Well, maybe not that one so much, but that one worked, and that one worked, and that one worked. So they wait for sunshine when they can do a lot of photosynthesis. So that mixing must be the trigger which provides the nutrients for them to come up to the surface. And then they wait until the sunshine comes, and then there's a massive bloom. They probably run out of nutrients and then die off and go back into the sediments, waiting for the next perfect time for coming. As far as wind speeds go, here's detected wind speeds on that axis. Here's the number of blooms that were detected. There was one, but it was calmer at that site. If you look at other data that looked at floor probe concentrations for blue-green algae, you only got a lot of blue-green algae when the wind speed was low. And these speeds are corresponding to little ripples on the lake surface, very light winds, nothing strong. Apparently strong winds will mix them in throughout the water column and take them away. And you won't have them as often as before. So what are these nutrient sources? It's intriguing to note that the majority of the blooms happen where there's a relatively huge shelf, at least in comparison to other parts of the lake. And on this shallow water shelf, you can have abundant zebra mussels and quagga mussels, mostly quagga mussels now, but I'm waiting to hear Kim talk about all this. You also have abundant weed growth. Both of them will secrete things or die off that will then get decomposed and release nutrients into that near-shore mud. And then the wind event will mix up that near-shore mud, shallow water mud, and provide the nutrients, which then you have blue-green algae blooms a day or two after that event. In support, along Seneca Lake, they've been taking pictures. I showed this slide last year as well, where there was a lot of weeds accumulating along the shore. Excuse me, let's back up. Where there's a lot of weeds accumulating on the shore. I said that, and I said, there's no weeds there. Where there's a lot of weeds accumulating along the shore, they're rotting and giving nutrients into the water column, lots of blue-green algae. In contrast, we'll say this correctly this time, where there's very little weeds along the lake shore, very little blue-green algae. So it suggests that there's some sort of link. And what's really intriguing to me is these weeds will accumulate in the downwind direction. So wherever the wind's blowing, you get accumulation of a nutrient source, which then can highlight where the blue-green algae are going to grow. So I get this idea, maybe it's coming out of the sediment someplace, so I'll run a really simple experiment. I'll take a bunch of flasks, I'll put Alaska Lake mud in the bottom of each one, each coming from a different site. And then I put on top filtered lake water. So there's no algae in there, just nutrients from the lake water, not a lot of nutrients in that lake water that I used. And then I waited 2 weeks. Every one of those flasks gave me really good blue-green algae blooms, even the mud taken from the deepest part of the lake. There's plenty of nutrients in those mud. I did swirl it up a little bit at the beginning, stimulated my own wind event, and then let it sit. So it's amazing what you can do in your office, right? Don't look at all this mess down here. That's just like the rest of me, like, you know, my hair's whatever. But there's the flash starting out, and there we are afterwards. So maybe there's something to what's going on in the mud, providing the nutrients for these things to bloom. I harp on this because if you look at the blue-green algae concentrations that you can measure on the near shore, no way can the normal nutrient concentrations in the water column support. There's just not enough. So you have to come up with an extra source, a huge source. And this might do it. This mixing event scenario might do it. I also then tried to test bubblers and ultrasonic vibrators the result of the study was I never really saw a good bloom to make a very conclusive test. And as a result, there was a few sites that were controlled. They were slightly elevated, but not in the thousands of times more concentrated in terms of blue-green algae compared to the ultrasonic devices or the sites which had aerators, these bubblers. Did the same thing for microcystin concentrations, the main toxin coming out of these things. Some of them had a little bit more than others, but there wasn't any real pattern to it. Mainly because whenever I was there, there was no bloom. What that means to me is if you want to get blooms out of your lake, just hire me. I'll go around to each dock every day. And then the blooms would disappear, right? Because apparently they don't like me. Anyway, who knows? So for blue-green algae, I still think these bubblers or ultrasonic devices might work. We just didn't have big enough blooms when I was there to really sample it. Never use a herbicide because you drink the water. Remove the organic matter from the sediments, especially the nearshore sediments. You can harvest the weeds and then take them out of the watershed. The nutrients can't come back in. If you have it accumulating along your lake shore, break them up, put them in a compost pile. Best if the compost pile is out of the watershed so it doesn't come floating right back in. Other simple things that you can do might work. We need to study and understand zebra and quagga mussels a little bit more. More importantly, we still have more nutrients coming into the lake than what's leaving. It's improved over the last 3 or 4 years, but we still have more nutrients coming in than what's leaving, and we can do something there to help clean things up as well. For 2019, I was just heard that Cuyahoga County is going to support my lake and stream monitoring effort. This is good. They're also going to allow me to put some data loggers that my colleague from physics, her students designed, which allows me to sense 4 different things, like temperature or salinity, or say the amount of chlorophyll in the water, or say the amount of blue-green algae chlorophyll that's there, or turbidity, or whatever I want to attach that output to voltage. What's really cool about these things is they all have their own cell phone. There's its antenna. So I can be sitting in my office looking at all this data coming in and get overwhelmed. But anyway, I'll get to test a few of those around. I'll also put some automated cameras and other things at some of these dock sites just to see if these things being blue-green algae blooms, are indeed fickle. Do they just last a year? No, a year, right? Do they just last a day? Maybe it's hours. Is it the same time of day? Is it not? Is it right after a wind event? So I'll have met stations at each dock as well to know if it did rain or if it did have a windy day coming onshore, which is more important than wind going the other way. And then Emerson funds will allow me to deploy the buoy again this year coming up. It's the last year of a 3-year grant, and look at some nearshore sites and put the temperature loggers out along some dock sites again and play with the drone. Hopefully I won't crash another one. They get expensive over there. So with that, I leave you. If you have questions, I don't know, I probably went way over time, so we should probably go to the next speaker. But anyway, do we have questions?
I've been text one question. Dr. Halfman, you indicate that phosphorus is coming from the Owasco Inlet. What is the impact of the southern wetland on holding historic P and then releasing that P during storm events? Do you sample phosphorus coming from the wetland?
I do sample phosphorus coming from the Owasco Inlet. It's just upstream from the wetland, so I really don't know what's going downstream from the wetland, but I'm pretty convinced that what Bruce has been able to do in installing retention ponds and other things in those wetlands have worked really, really well, so that the amount of phosphorus coming down that inlet is significantly reduced. One more comment I would have is there's proportionally more coming out of the southern inlet only because that inlet is huge. It covers more area than any other watershed coming into the lake. Proportionally smaller amounts come in from all the other ones. Another question.
Another question for John. Thank you, John, by the way. For Dr. Halfman, would harvesting of BGAs at time of bloom be practical, and how much organic material would this yield? Do we know? If not, is it worth trying?
I think it is worth trying. Is it practical? I don't know. They can skim oil off the surface of water, so they probably can skim blue-green algae off the surface of the water as well. I've never seen the technology, though, used for blue-green algae. In terms of the quantity of material that you can take out of a lake from harvesting like that, it would be huge, because these blue-green algae blooms are very significant. They're orders of magnitude larger in terms of concentration than any other algae that you find in the lake at any other time of the year. So it's just like harvesting the weeds and take them out. If you could harvest the blue-green algae and take them out, you'd probably be doing some good.
Go ahead.
This is for John. Can someone address the impact of torrential rains versus wet years of normal rainfall? Does this change the nature of the needed interventions for the BMPs?
Yes. No, so last year, Seneca Lake had a torrential downfall on Lodi Point. The only place that got 14 or 15 inches of rain in one day was Lodi Point. If you look at the delta at Lodi Point, every cottage, every propane tank, every car moved because of that flood, along with everything else that washed in the lake. There was a 2-week period in Seneca Lake when they had boating restrictions, because there was trees and other things floating in the water column. You really don't want to drive into a propane tank, for example. It's not recommended. So you can think of all the nutrients and other things that are coming down in that same event. These are events that are probably driven by climate change, global warming. Very small, isolated, massive things.
Another question, can you explain the bubblers and ultrasonic vibrators, how they're supposed to theoretically work?
Okay, so blue-green algae, they like to float right at the surface, because then they can do a lot of photosynthesis where there's a lot of sunlight. The bubblers will emit bubblers from the lake floor up to the surface and literally mix the water column. And just like waves, they might take that surface accumulation of blue-green algae and mix it through the water column. So it's not really concentrated at the top, but it's evenly mixed throughout the water column, and the overall concentration will go down a little bit. In contrast, the ultrasonic vibrators, what they'll do is, for blue-green algae to float, they have little gas vacuoles in their cell wall that they can fill up with gas and then float, because they're like little life preservers. What the ultrasonic vibrators will do is disrupt those little gas vacuoles so they can't hold gas, so they can't float. So they never can do that, accumulating at the surface.
Okay, another question. Can you explain the nutrient component of the septic monitoring program, since our concern is nutrients?
Nutrient component of the septic monitoring
I don't
believe we have a septic monitoring program.
Cuba County has
That monitors nutrients.
well, we have a septic inspection program that is that other counties do not have, and that is on the lakeshore properties. It's every 2 years, and then every septic system in Cuba County, depending on their distance from the water bodies, gets inspected by a certified inspector. That's the only monitoring program I know of about septic specifically.
The data that I will always repeat is that if you could put a sewer system around the lake and treat all that waste by a municipal wastewater treatment facility, it will radically decrease the amount of nutrients that eventually get into the soil and might make it to the lake. So you might think about it, even though it costs lots of money.
Great. We have a few other questions, but could you take those up with John afterwards? Because you've got to keep moving along here. Appreciate it very, very much. Thanks, John.